Good evening, everyone. This is Mr. Steele. We're going to be working through the next set of video solutions, this time attacking, I think it's problem set 21, that's focused on implicit differentiation and the technique itself, executing it, using it with different sorts of relations, using it to write equations with tangent lines, all sorts of good stuff like that. Some of our questions will go a little bit further and ask you to work to find one or both of the coordinates, and some of them will just ask you to compute through, but possibly use the product rule, chain rule, or quotient rule in the context of the problem that you're doing implicitly. So with that said, rather than beat around the bush and get things started here, why don't we jump right into the first problem. Okay, the first problem we're going to look at is number 1 on the assignment, and that's simply because I feel like there may be some of you out there who just want to see the technique explained again, kind of from the beginning. So I've chosen the simplest problem on the entire assignment. In fact, the problem that you could do other ways, if you so decided. I'm going to use this to kind of illustrate the technique. So reading those instructions, it says to compute dy dx, in other words, the derivative of y with respect to x, using implicit differentiation, we are to show all work, obviously, and write all our answers in an appropriate form. So to get us started here, obviously there's going to be some challenges here, but what we're going to be doing is we want to compute the derivative with respect to x of this entire expression. What's going on here is we don't have a traditional relationship defined like we have always in the past. Something like y equals x squared plus 5, where the dependent variable is explicitly defined as a function of the independent variable. So that's not what we're looking at here. This is implicit because both x and y are on the same side. Now in this particular equation, you could transform this into an implicit equation, but that's not how it's presented, so I'm not going to attack it that way right away. Instead, I just want to think about what this is going to entail. So to start things off, let's just kind of go as far as we can before anything pops up. So in here, if I were to differentiate this using derivative rule properties, we'd first have the derivative with respect to x of x cubed. Then we'd have minus the derivative with respect to x of y squared. And that's all equal to the derivative with respect to x of 10x. Now in computing these derivatives, 2 of the 3 are really simple and don't require any actual work. The derivative of x cubed with respect to x is going to be 3x squared. And the derivative of 10x with respect to x is going to be equal to 10. So 2 of the 3 are there. Our big issue here is that we need to compute the derivative with respect to x of y squared, which has no x in it, which complicates things for sure. So what I want to do, as we did in our lecture during class, I want to focus our attention on that expression for 1 second. And again, this is something we've done in class already, so you've seen it, but for the moment this is just an opportunity to talk through it one more time. So we are trying to figure out what is the derivative with respect to x of y squared. And think about why this is even necessary. So first of all, a couple things to point out. So things to think about here as we get started. The first thing to think about is simply what is the derivative with respect to x of x squared. Because y squared and x squared are very similar to those two things. And of course you know that derivative is 2x. So your ideal here would be to realize that the derivative must involve 2y. There's just a little bit more going on there. So here's kind of my thought process. I'm going to call this expression g of x equals y squared. And specifically, because we know x and y have some dependent relationship, as in one x value, or the y values themselves are always dependent on the x values themselves, you can think of y as being equal to some function f of x. In other words, this function g of x is actually equal to the quantity f of x squared. Yeah. Now bringing that up for a second, hopefully this helps you see really fast what rule it is we need. This is going to require the chain rule. We have a function f of x, which we know we're calling y otherwise, being squared, which means that we need to use the chain rule. The outside of this expression, like we'll just go out for the moment, or actually we'll go g of u would be equal to u squared, and then u is equal to f of x. And with those two pieces in place, the derivative of g with respect to u is 2u, and the derivative of u with respect to x is just f prime of x. And bringing those two pieces together and bringing it all back, this derivative, g prime of x, which hopefully this isn't going to, here just a second, make a few switches to make this a little bit spaced better. So in looking at here, g prime of x is going to be equal to 2u times u prime. But remember, at the very beginning here, didn't we say that f of x was just a way to think about y in a familiar x-based system? So in reality, if y equals f of x, that would be the same thing as that would also tell us that y prime is equal to f prime of x. So this derivative is really 2 times y, because f of x is y, times f prime, which we call y prime. So in a sense, this expression is going to be the answer to that question up above. It's 2y, y prime. With the 2y representing the derivative we expected, stuff to the second power has derivative 2 times stuff, and then times the derivative of the inside, and our inside just happens to be simply y. So with that in place, we can actually pull that derivative over to our equation on the left. We found that the derivative with respect to x of y squared is equal to 2y times y prime. And in our case, y prime is just another way of saying dy dx. They're just different notations for the same thing. With those in place, of course, we have more of this implicit derivative to look at. We have 3x squared minus 2yy prime equals 10. Now from here, we need to get the 2yy prime to be by itself. There's 2 ways to do it every single time, depending on where you move it over. What I'm going to do might seem kind of clunky, but I want to get this over to the other side. And then I also want to subtract 10. When I do, I end up with 3x squared minus 10 on the left. On the right, I just have 2y, y prime. And if we want to get y prime, otherwise known as dy dx by itself, we just need to divide. And doing so will lead us to y prime, which we call more formally dy dx. So it's really explicit what variable we are differentiating with respect to. Dy dx is equal to 3x squared minus 10 over 2y. And there is the answer we were looking for. That represents the slope at any point x comma y on this particular curve. Now, having said that, I mentioned at the very beginning that there is another way to approach this particular problem. That isn't going to be there every time, but since there is a second way that we could approach this that's more or less easier, it might be worth pointing out that we can check to make sure that we did in fact find the correct answer. So what I'm going to do here really fast is I'm just going to clean out some space. I'm going to look at the alternate technique that we had available to us, because there is in fact an alternate technique. So specifically, let me point out to you that if x cubed minus y squared equals 10x, then y squared is equal to x cubed, I did it right, x cubed minus 10x. And then specifically, y is equal to plus or minus the square root of x cubed minus 10x. Right, that's just solving for y, basically. We only had one y in there, so it's easy enough to just solve. Now from here, we can compute the derivative with respect to x one more time. Keep in mind that this plus or minus 1 is just like having a scalar of plus or minus 1, so it's just going to be a number. As far as derivatives, we'll have d dx of y, which is dy dx, or y prime. On the right side, we have the derivative of plus or minus a square root. That's going to be 1 over, or plus or minus 1 over 2 square root of x cubed minus 10x. And then times the derivative of the inside, and the derivative of the inside is 3x squared minus 10. Hey, look at that. Does that not look a little familiar? It should. So with that in place, we've got a couple things here. I'm just going to make some cosmetic changes. I'm going to move that plus or minus down below. Like, forgive me for a second, but it will work. This will be 3x squared minus 10 over 2 times plus or minus the square root of x cubed minus 10x. Now maybe you could see why I put the plus or minus in the position that I did. Maybe you can't. If you're looking, my motivation was right here. We said y is plus or minus the square root of x cubed minus 10x, and right here we have plus or minus the square root of x cubed minus 10x. That means this expression is equivalent to 3x squared minus 10 over 2y. And those, my friends, are identical expressions. And of course they are, because we're getting the same derivative. One's just written explicitly, one's written explicitly or implicitly. We want to get the implicit one, that's the focal point of our work here, but we could absolutely do the explicit version just as well. It'd be a choice if that was given as an option. So in any event, there's the technique. You can see that origin of implicit differentiation grounded in the chain rule. You can see an organization system as you're getting started and getting comfortable with what you're doing. And you can see that it works no matter which way you have it. If explicit is an option, it works just as well as implicit. So there's question number 1. Hopefully a really good overview of the technique itself and something that helps propel you forward through the rest of the assignment. Okay, next, this brings us to question number 2. I think question number 2 is actually a very straightforward question. It's just guilty of looking a little clunky and feeling a little awkward when you do that first differentiation step. So we're doing the same thing. We want dy dx, otherwise known as y prime, and we want to show all work and write an appropriate answer. So in here, as I did before, I'm going to write that first step, which I'm hoping that you'll consider essential. I like this first step because it establishes what we're differentiating with respect to, and that gives us a little bit of freedom if we so choose to write y primes rather than dy dx's through the rest of our work. So in looking here, a couple things to point out. The derivative of square root of x, we've talked about this before, is the derivative of x to the 1/2 power. That's 1/2 x to the negative 1/2. And I'll remind you, that's 1/2, or 1 over 2 x to the 1/2, also known as 1 over 2 square root of x. So if you haven't memorized this and committed this to memory, then enjoy doing 3 extra steps. Nothing wrong with it, just take a little bit longer to get there. So it might not look as elegant as what my answer might. So with this in place, when we go to differentiate, again, I'll break it down really carefully, more so than I think I even did in the written solutions. We'll take the derivative with respect to x of square root of x, the derivative with respect to x of square root of y. That's going to be where the implicit work comes in. And it's all equal to the derivative with respect to x of 5. So once again, 2 of these derivatives are very easy to compute. The derivative with respect to x of 5 is 0. It's a constant function. Its slope is 0. The derivative with respect to x of square root of x, well, it's literally written up here. But otherwise, you could just do it in whichever technique you have. Or just recall it from your mind. Now, our challenging one is this guy over here. And truthfully, I don't want to go through the full soliloquy derivation where we go and work off on the side and then pull it back in. I think that we should be able to move a little bit faster because it's a very basic function. It just has a y in it. So why spend extra time deriving things in a difficult way when differentiation isn't that hard? So in here, let's think about it. Let's start with this. The first question I always ask myself when I'm differentiating implicitly and I get to an expression to take the derivative of, I always ask myself, well, what would the derivative be if that was an x? And clearly here, because it would then therefore be identical to the first thing we took the derivative of, this would be 1 over 2 square root of y. It's the same exact function, it's just got a y in it. The only thing that changes then is the chain rule. We also have to multiply by the derivative of the inside. And the derivative of y, we know as dy dx. We can also, just for simplicity of our work and computation, call that y prime. From here, we've set up an equation that works great. We have x's and y's in there, as well as a single y prime. So our job from this point is to go forward, or move forward, and actually isolate the y prime. So the first move I'm going to do is I'm going to subtract 1 over 2 root x from both sides. That's going to give me 1 over 2 root y. Y prime is equal to negative 1 over 2 root x. And from there, if I want this by itself, I need to get rid of the 1 over 2 root y. So I'm going to multiply both sides by 2 root y. That was terrible square root. There we go. When I do, I get y prime on the left is equal to negative 2 root y over 2 root x. And hey, the 2's divide out. That leaves us with our formal version of the answer, which is negative square root of y over square root of x. Or if you're obsessed with rationalization or rationalizing the denominator, you could also write this as negative square root of xy all divided by x. Either of those two answers would be acceptable. So in here again, nothing very difficult, just you had to be able to juggle some things and take some derivatives that looked a little awkward, and then solving it went pretty fast, but it was easy to make a small mistake because of the apparent flipping that you were doing. So that hits question number 2 for us. Okay, third, we're going to look at question number 4. So saying third was probably not the ideal way to start the problem. But we're once again looking for dy dx, and we've got an expression to go through. In this one, there's going to be a particular term that's going to be our challenge. So we'll deal with it when we actually get there. So a couple things here. Before I start anything else, I'm going to first point out to you that the term that's going to give us the biggest trouble on number 4 is this negative 7xy squared. So I'm going to start by rewriting this very slightly differently, or with a very slight difference, as x to the 5th plus negative 7xy squared. That way we've got this minus 7x attached. All plus y cubed equals 42. So I'm starting there, and that's what I'm going to differentiate with respect to x for. So with that in, of course, doing the simplest terms, and I'm just going to focus on those ones first. Derivative with respect to x of x to the 5th is 5x to the 4th. The next one, yeah, that's going to be a little bit of work. We're going to have to play a little bit of a game there. We'll deal with that. Plus now we have the derivative with respect to x of y cubed. So y cubed's derivative would be 3y squared times the derivative of the inside, which is y prime. And then on the other side, the derivative with respect to x, or any variable, of 42 is 0, because it's a constant function. So once again in here, one piece really draws our attention in. It's not, though, this time the pure implicit one. It's one that involves both negative 7x and y squared. This term itself is going to actually require the product rule, because we're really multiplying two different functions together. One has only x as its variable, and is the function negative 7x. The other one has y as its variable, and we're calling y squared. So with that in mind, I'm going to go up here and do the product rule piece separately, just so it's really clear what's actually happening here. This is usually the problem that people make errors on in the Term 3 standard quiz, in fact. People just forget about the product rule part, or they speed through it, or they drop a y prime. Like, those things happen when there's heavier differentiation techniques at play. So in this particular situation, our product rule, we are taking the derivative with respect to x of negative 7x y squared. That's going to be equal to the derivative of the first. Shoot, let's do it this way. I think this will be better. The derivative with respect to x of the first times the second plus the first times the derivative with respect to x of the second. So there is our product rule. I mean, it's pretty crunchy. There's a lot in there. But not all of these differentiations are difficult. Derivative with respect to x of negative 7x is just negative 7. So we get negative 7y squared. On the next one, we're going to get negative 7x times the derivative of y squared. And we've done this one before on the first problem. This is just going to be 2y times the derivative of the inside, which is y prime. So with that in place, there's our product rule term. I guess we could simplify it a little bit. We could write this as negative 7y squared minus 14xy y prime. So only a y prime on the one term. Keep in mind the reason for that is we only differentiated a y expression right here. The first one we were only differentiating the line negative 7x. So with this expression ready, we can now pull it back into our equation. In fact, I'll do exactly that. Negative 7y squared minus 14xy y prime. Pulling the other ingredients into the scenario here. 5x to the fourth minus 7y squared minus 14xy plus 3y squared y prime all equals 0. Now once again, we want to get y prime or dy dx by itself, so that way we can isolate it and solve for it. We're trying to get that derivative expression in there. So I'm going to add this one and subtract this one to the other side. So I'm going to move a little quick through it. I'm hoping that's okay. I don't think it's too bad. It's going to give us that the left side is equal to positive 14xy minus 3y squared all times y prime. So you might have noticed that I did another move. I basically moved the two expressions right there and there over, but I factored out a GCF of y prime automatically, just to make sure that I didn't have to write another step for that. From here, to simplify this all out and finish it, we will divide both sides by this parenthesis, or by this factor. When we do, we're going to get that dy dx is equal to 5x to the fourth minus 7y squared. And it's all divided by 14xy minus 3y squared. But if you wanted to, you could also factor out a GCF from that expression itself of y. And then we'd have y times 14x minus 3y. Doesn't matter if you choose to or not, but since we're here, we might as well do it well. So in this case, the big addition was the presence of the product rule. And again, we were just careful here. We made sure to isolate and remember that we were differentiating with respect to x each time. If it was an x, it was easy. If it was a y, we had to include the y prime and use the chain rule. So there is question number 4. Okay, that brings us then to the final question we're going to look at from the first section, and that is question number 6. And question number 6 isn't what I'd call a particularly difficult question. It just involves the chain rule in a really heavy way, and not just the implicit differentiation built-in chain rule way. So our expression up there that we're going to differentiate is the square root. Actually, I'll write it one time here. We're going to take the derivative with respect to x. We're keeping that with respect to x again. Of square root of 7y cubed plus 11. That's all going to be equal to the derivative with respect to x of x over 2. And since we're here, a couple little things to point out. X over 2 is the same thing as 1/2 x. So the right side is going to differentiate to 1/2. On the left side, that's where the heaviest lifting is going to show up. We've got to do the derivative of this square root of 7y cubed thing. Got to deal with this mess. In order to do that, that's going to require the chain rule. And as I said, it's not just the implicit version of the chain rule. So for that, I'm going to go over to this side. I'm going to call this, as I've done before, f of u, even though it's not necessarily a perfect name for it. We're just going to play along for a second. So we're going to let f of u be the square root of u, and then we're going to let u equal the inside 7y cubed plus 11. So from here, if we want to differentiate these things with respect to x, which is exactly what we want to do, by the way, let's see. We're going to have f prime of u equals 1 over 2 root u, so nothing too bad right there. On the other side, though, if we take the derivative, we're going to get 21y squared, but because this was a y that we were differentiating, we need to use the chain rule and multiply by y prime. So technically, this is almost an included chain rule, or a chain rule built into the function that we already had. With those two pieces in place, if we multiply them together, we'll get that the derivative is 21y squared, because again, we're just multiplying these. We're going to get 21y squared over 2 square root of u, and that is exactly what we need to multiply into our equation. Oh, except for one thing. Can you see what I forgot? Forgot something really fast right there. I dropped the y prime. It needs to be there, so I've got to include it in there. Otherwise, we'll have nothing to save or share or solve for. So all of this is equal to 1/2. We mentioned that earlier. From here, we need to solve for y prime. So a couple different ways to get there. I'm going to go with the one that is fastest. So I'm going to multiply by everything except for the y prime, but in a reciprocal, because I want to get rid of the denominator and make it move over. I think on my written solutions, I actually did a cross-multiplying sort of technique, or at least it looked that way. So moving some things over, the first thing I'm going to do is multiply both sides by 2 square root of, 7y cubed plus 11. And that's kind of a nice first move, because notice the 2's divide away. Second, I'm going to divide both sides by 21y squared. And that's going to leave us with the equation y prime, which we know as dy dx, is equal to, 2's divided away, square root of 7y cubed plus 11, all divided by 21y squared. And we weren't expected to do anything else here, but just find the derivative. But I think you can probably see where the challenge lay here, where the challenge fell in this problem. We had to deal with some chain rule built into the expression that had a y inside, which created its own little double situation scenario. Everything else was just a matter of trying to move things to the correct side and keep track of what was what. Okay, this next brings us to question number 9. And I think question number 9 does a really good job of not just practicing implicit differentiation with a good level challenge problem. I think it also does a really nice job of bringing up the idea that that original equation isn't something that's just going to lead us to our derivative. It's actually something that guarantees or gives us very important information about the function itself and the behavior of the curve that we're looking at. Can't call it a function. So in here, we're told to use implicit differentiation to compute dy dx and then find the slope of the curve at the indicated points. So we eventually want the slope at a given point. So we'll deal with that when we get there. It's like we'll cross that bridge when it arrives. So to start with, we're going to differentiate with respect to x this entire equation. And on the left side, I see it's pretty simple. We have x's and y's separated in there. They're not on separate sides, but they are separate, so it's going to be easy to just differentiate each term using the power rule. And then on the right side, we have 3xy squared minus 40, and product rule is strong in this one. Like that's going to be a product rule. We have 3x times y squared. So we are going to end up dealing with some product rule here, which means this isn't a trivial differentiation problem. So in looking at our ingredients, we'll do as much as we can, as fast as we can. And again, we'll pay everything that we're skipping here later. So derivative with respect to x of x squared is 2x. The derivative with respect to x of y cubed is going to be 3y squared. But because it's a y and x are connected, and we need to use the chain rule and multiply by y prime. On the right side, again, I'll be really careful with the product rule. We're going to have the derivative with respect to x of 3x times y squared plus 3x times the derivative with respect to x of y squared. And then everything is minus the derivative with respect to x of 40, which would just be minus 0. So differentiating and cleaning up anything that we can, the left side remains the same. On the right side, the derivative with respect to x of 3x is of course 3, the slope, because that was just a line. And then plus, we have 3x. We've done this derivative with respect to x of y squared already in these video solutions. This is equal to 2y times y prime. So over here, we have 3x times 2y prime, which means it's equal to 6xy y prime. And of course, all minus 0 means we don't need anything else there. To wrap up this derivative part, we need to get everything over to the same side. So we actually have two equally time-consuming options. We could either subtract 2x and subtract 6xy prime, or we could subtract 3y squared y prime and subtract 3y squared. So for the sake of simplicity, I'm going to subtract 3y squared y prime over, and then I'm also going to subtract 3y squared. So cleaning some pieces up here, we're going to get 2x minus 3y squared is equal to 6xy. Yep, 6xy minus 3y squared. But both of those were multiplied times the y prime. And of course that leads us to our answer. We were looking for dy dx first. It's going to be 2x minus 3y squared over 6xy minus 3y squared. So step 1 is complete. So to get there, nothing new. No new differentiation skills from the implicit work we've already been doing today. The only thing that was presenting a dilemma was simply the fact that we had the product rule mixed in there. And it was a fairly lengthy problem. There was a lot of differentiation happening there. Now that we have it, though, that leads us to the second portion of what's there. We are told to find the slope of the curve at the indicated coordinate, or coordinates. So looking up here, we need to look at what we are told. If we're given both x and y, the problem's done. All we have to do is plug it in. But in this case, we're only provided that y equals negative 2. And this is one of those pieces that sometimes confuses even the best students. It's easy to just look at this and go, man, there's just nothing there. There's so little. Where's my x value? And the answer is you don't have it for free, but you can find it without much trouble. Because here's the thing. If y equals negative 2, then look at our equation. Everywhere where there's a y can be replaced by negative 2. That's going to make our equation x squared plus negative 2 cubed equals 3x negative 2 squared minus 40. That means x squared minus 8 is equal to 12x minus 40. And moving some pieces over really quickly, not to trivialize it, but it goes really fast. X squared minus 12x plus 32 is equal to 0. Doing some quick factoring, not trying to do too much here, but some quick factoring. We get that x minus 4, x minus 8 equals 0, and lo and behold, we actually get two separate x values in this case. That can kind of feel strange. It might make you think that you've done one incorrectly. Unfortunately, you haven't. There's just two possible answers here. We have two potential slopes of the curve at that indicated coordinate. In fact, we can graph this one on Desmos right after we finish the problem and see if this is at all accurate. Hint, it is. So in here, let's do each one separately and show you what that would look like. So first, if x equals 4, we're at the point 4 comma negative 2. That's going to lead us to a slope of dy dx equals 2 times 4 minus 3 times negative 2 squared all over 6 times 4 times negative 2 minus 3 times negative 2 squared. That's going to be 8 minus 12 over 24. Negative 48 minus 12 is minus 60. It's going to be negative 4. Wait, did I do that right? That's going to be 6 times 4 is 48. Oh, no, I did that wrong, didn't I? Looks like that's going to be 48 minus 12. Let's see, 24, negative 48. No, I did it right. Minus 12 over negative 60 is 1 over 15. So one particular slope is 1/15. On the other hand, we also have a second slope that we could potentially get. It's going to be fairly similar. I'm just going to move it down to here. So the other option is that we could have the point 8 comma negative 2. If we do, dy dx is going to be equal to 2 times 8 minus 3 times negative 2 over 6 times 8 times negative 2 minus 3 times negative 2 squared. So that should have been squared as well. Cleaning pieces up here, that's going to be equal to 16 minus 12 is 4. That's 48 times negative 2 is negative 96. Minus 12 is minus 108. And that leaves us negative 1 over 27. So in this case, we actually ended up getting two slopes, because supposedly there are 2 points where the y-coordinate is equal to negative 2. So as I said, let's let Desmos tell us if this is accurate or not. Might as well take advantage of some extra space here in time. Okay, so our curve itself, x squared plus y cubed. And this is one of those cool things Desmos can do that your graphing calculator just does not have any hope of being able to do. 3xy squared. Okay, so our question was, are there 2 separate places where, what was it, y equals negative 2? There's one right there. And one right there. And notice looking in here, I know it's not the greatest picture in the world, especially with those pieces in. But notice that one of them does appear to have a negative slope, and one does appear to have a positive slope. So it looks like we've done a good job of identifying 2 separate values, and we've been able to solve this question. And keep in mind, this was a challenging question, not only because there were 2 pieces here, but the product rule was built in. There was just a lot to do on this problem. But you're able to work through it fairly straightforwardly if you're just patient and you trust the information you get when you're solving things through. Okay, that next brings us to question number 10. This may be the last one that I get to do right now, because I've got somewhere I have to go tonight. I'll have to pick it up later, probably tomorrow. In this case, this was a question that I actually forgot to write into the written solutions when I was, putting the questions together to work through on the computer. So I'm going to have to add this to the end of the assignment and do it again. So this will be a fresh run through this problem. And I will tell you what, this is the most plus question. This is the single hardest question, I think, on this entire page. This is the one, and it's not difficult conceptually, it's difficult computationally. You have to do some work here, and it's a challenge to do. So let's jump in. So first of all, we want to take the derivative of this thing. The nice thing that we have here is we don't have to do any fancy algebra to figure out what x or y is equal to. So at least that's nice. So we want to take the derivative of x plus y cubed equals x cubed plus y cubed. Now, interestingly enough, the cool thing here is that the right side's actually really easy. The right side is 3x squared plus 3y squared, but because of the y, times y prime. It's that left side that has to do a little bit of work. And as we've done in the past, you can kind of see we've got something interesting happening on the inside. So what that's telling me is if we're trying to take the derivative with respect to x of x, I get parentheses in there, x plus y cubed, that makes me think of the chain rule. So this isn't going to be perfect because there's not really names for these things, but I'm going to call them a name and then go from there. So I'm going to let f of u equal u cubed, and I'm going to let u equal the inside x plus y. Just trying to motivate what the derivative is here. So from there, if we want to take the derivative, that's going to be 3u squared for the outside. And derivative of the inside, be careful. The derivative of x is 1, and the derivative of y is 1y prime. So I'll even write that in there. Bringing the two pieces together then, our full derivative is going to be 3x plus y squared times 1 plus y prime. So over on that left side, we're going to have 3x plus y squared, 1 plus y prime. So this is a great start. Like, just getting into that far into the problem is a fantastic move and an impressive move for sure. But the difficulty here is our job is always to isolate y prime. But we've got a y prime trapped in this factor on the left side. And it's not clear exactly what you want to do. If you were to divide both sides by 3x plus y squared, you'd end up with really messy terms for both of these two terms themselves. So instead what I'm going to do is a strange move, but it's going to be the one that gets us through this problem the fastest. I'm going to distribute 3x plus y squared to each of the two terms in that u prime factor. When I do, I'll get 3x plus y squared plus 3x plus y squared y prime is equal to 3x squared plus 3y squared y prime. Now a couple moves here to go through, and I hope this is going to be okay. Always trying to keep things as clean as possible while working through. Notice that all four terms have a 3. I'm going to go ahead and multiply the entire thing by 1/3. I don't want to write it again though, so please forgive me for just, what is that word, nerfing the 3's as I work my way through. There we go, there's our stuff. We now have this isolated a little bit more, and from here this is just a regular implicit differentiation problem. This is now x plus y squared I'm going to subtract 3x squared from both sides. Sorry, let's do this over here. So minus 3x squared. On the right side, I'm going to subtract the x plus... Oh, I don't need the 3, do I? Dang it. It's not minus 3x squared, it's minus x squared. On the right side, I'm going to have y squared, y prime, minus x plus y squared. And this whole thing on the right side has a y prime. Now from here, there are ways you could simplify these expressions, by the way. I'm not going to worry about them for right now. I'm just going to put what I'd call the cleanest version, or the fastest version of this answer. You could divide both sides by y squared minus x plus y squared. And if you did, you'd end up with the derivative. Totally correct, by the way. No simplification necessary. X plus y squared minus x squared over y squared minus x plus y squared. So this is a great final answer. And getting there was quite a battle because of all the work that was required with the chain rule, and also this really annoying kind of distribution or unfactoring step that we had to do to proceed forward. But I do want to point out to you, as I can every single time there's something interesting, this expression is actually interesting because both the numerator and denominator feature what we would call a difference of squares. In fact, each one has something of the form a squared minus b squared. And of course, we know those things factor to a plus b, a minus b. And I'm just curious, because we're looking at it, whether or not that might possibly lead us to something that's even simpler. So let's give it a shot. In the denominator, we have x plus y being squared, and then subtracting x squared. That's going to give us x plus y minus x plus y plus x. And then in the denominator, we have y minus x plus y squared. That's going to be y minus quantity x plus y, so y minus x minus y, times y plus x plus y. In looking at these ingredients, the question is, does anything actually simplify away? Well, as I look at the pieces, the top one, the x's do go to 0, and we're just left with y quantity 2x plus y. Down below, the y's go away, and we're left instead with negative x quantity 2y plus x. So did that get better? Yeah, I mean, I think that's a lot better. It's a lot easier to see, it's a lot easier to plug into than it was at the very beginning. But hey, neither answer's wrong. Both of these are equally adept and equally skilled answers to get there. In any event, though, let me just remind you that question number 10 is the biggest challenge computationally, I think, on this entire assignment. So don't be stressed if it is a little bit frustrating. I know you can handle it, though. Okay, finally, that brings us to question number 12. I think 12A may be the last one that I'm going to be able to work through. So in 12, you're given a table of values, which seems like a weird match for an implicit differentiation problem set, but no worries, we should be able to handle this. And in fact, looking over here, they tell us only that the twice differentiable function f of x has values in that table, as well as values of its derivatives, f prime and f double prime. So I should probably fix those instructions. So in here, for 12a, it says let 4x squared plus, here, I'm going to write this down just so I can focus on it. 4x squared plus f of y equals 3y plus 2. So as we look at this for the first time, let me point out to you that this might seem like this isn't going to work at all. Like there's just nowhere to go because of that f of y. In your mind, you might be saying, well, we have a table with values of f of x and x, but we don't have anything involving y. But the truth is, it doesn't really matter. If I tell you to evaluate f of y at, let's say, x equals 2, or let's pick x equals negative 3, that's the same thing as saying, what is f of negative 3? And f of negative 3 is right here as negative 1. It doesn't matter that x is our variable, because the variables are just names. F is behaving this way, and we could just substitute the name of that thing. It's like if you accidentally called me Mr. Shanning. In addition to taking that as a compliment, it wouldn't necessarily change what answer I'd be able to provide for you. I might just be a little annoyed with you or roll my eyes or something, or then call you by the wrong name. It's not going to change anything, it's just a cosmetic difference. So in fact, this isn't going to do much as far as evaluation. We should be able to pull the values directly out of the table, but for the moment, it just looks a little bit awkward, hence the reason I wrote the question. So let's go through here. We're supposed to find dy dx at a particular point. In fact, our point is negative 2, 6. So let's go ahead and see what happens when we take the derivative with respect to x and see if we can pinpoint what's weird. So derivative with respect to x of 4x squared, that's going to be 8x. The derivative with respect to that's going to be a challenge. Let's play with that in just a second. That's the newbie. Then on the right side, we'll have the derivative with respect to x of 3y. That's going to be 3y prime. Or you know what the heck, we're here. Let's go the derivative with respect to x of 3y. And then, of course, plus 0. So looking at our derivatives here to proceed forward, obviously the 8x isn't the biggest problem. On the right side, the derivative of 3y, well, let's think about that. The derivative of 3x would be 3, but since there's a y, we need the chain rule, so we're going to have to multiply by y prime. On the left side with that other one, we need to think about it the same way. The derivative of f of x would just be f prime of x, but there's a y inside, so we keep it there. And then, of course, because of the y, we need the chain rule, so we multiply by y prime. This is our derivative expression that works for this particular curve. So from there, all we need to do is pull everything to the same side. 3 minus f prime of y, all times y prime. It's going to lead us to y prime, also known as dy dx, being equal to 8x over 3 minus f prime of y. And then at this point, we remind ourselves what it is that we're evaluating at, or where it is we're evaluating at. We're evaluating at negative 2, 6. So if we plug in x equals negative 2 and y equals 6, then dy dx is going to be equal to 8 times negative 2 over 3 minus f prime of 6. And the nice thing here is now at this point you can tell, you can't even see that this was f prime of y anymore. We have the y value plugged in, now it's just f prime of 6. And f prime of 6 is negative 8. It says so right up there. And with that in place, we get negative 16 on top, 3 minus a negative 8 in the denominator, and we get our final slope of negative 16 over 11, just by plugging in. So again, as I looked at this question, I don't think it's as difficult as you might have given it credit for. It definitely looked more challenging than it was. The key was taking the derivative of f of y, and then realizing that our table, though given in values of f of x and its derivatives, could compute f derivatives and values for f of y just as well, if we just had a y value that happened to be in our x values. So again, a little more challenging looking than it actually was to do, but a good question nonetheless. Okay, next that brings us to question 12b. Let a of t equal f of 16 over t plus 3. Is the graph of a increasing or decreasing at t equals 5? So first of all, in looking at this expression, we've got stuff shoved into f of x. We've got a 16 over t cubed in there. This is screaming to me that we need to use the chain rule. So I've got chain rule in my mind. In fact, doing a quick little full derivation of the chain rule, I'd let a of u equal the outside, which would be f of u. The inside would then be 16 over t plus 3, which, if you're going to be concerned about differentiating, is the same thing as 16 times t plus 3 to the negative 1. Taking the derivative of each piece, a prime of u is just f prime of u. U prime is going to be negative 16 over t plus 3 squared. And now we've just got to multiply our pieces together. We'll get our full derivative, a prime of t is f prime of u times u prime. So if we go in and want to figure out what the slope is at 5, so we can talk about increasing or decreasing, and I should have pointed that out at the beginning. Since we're asking about increasing or decreasing, that tells me I want to know about the sign of f prime. So I should have said that earlier. I apologize. So a prime of 5 is going to be equal to f prime of 16 over 8 times negative 16 over 5 plus 3, or 8 squared. Cleaning our pieces up here, that's going to be f prime of 2 times negative 16 over 64, which is negative 1/4. And f prime of 2 is negative 3. Negative 3 times negative 1/4 is equal to 3/4. And I'll point out to you that 3/4 is clearly a positive number. That tells us that a of t is increasing at t equals 5. Really easy to accidentally say t equals 2, by the way, just because you looked at the table at 2. But remember, 5 was the t value we were looking at for a. So a is increasing at t equals 5, and our reason is very simple. It's because a prime of 5 is greater than 0. And there is our work for 12b. Okay, third, in 12c, we're told that g of x is equal to this expression, so I'll copy it down so we have it. 3f of x plus kx squared, so we got one of them scalars in there, all minus 7. Then it says g has a point of inflection at x equals negative 3, and we want to know what is the value of the real number k. So a couple things here. If there's a POI at x equals negative 3, then we know that a POI means that the second derivative has to change signs, among many different things. But in here, because we're not going to be able to look at the sign change itself, and because we're given twice differentiability, if the second derivative equals 0 there, it's going to have to change signs somewhere in that interval. So therefore, that would be the same thing as us just saying, we want g prime of negative 3 to equal 0. That's going to satisfy our need for what's here. We just don't have any other information to be able to guarantee any other way that the sign actually changes. So to get here, we need to look at the second derivative. So a quick journey to get the second derivative takes us first through the first derivative. It's going to be plus 2kx. And then it takes us quickly to our second derivative, which is 3f double prime of x plus 2k. Now from here, we said that our next piece of information was that the second derivative at negative 3 was equal to 0. That means that g double prime of negative 3, which is equal to 0, is equal to 3f double prime of negative 3 plus 2k. So simplifying and plugging in some information, f double prime of negative 3, it says right here is 19. This is 3 times 19 plus 2k, and we know that sum has to equal 0. Well, 3 times 19 is 57, and 57 plus 2k has to equal 0. And without further ado, that means k is going to be equal to negative 57 over 2. And I'm going to slide through that algebraic step just a little bit to save a little bit of time, because there's a chance for me to actually finish this before I have to leave. Okay, 12D. 12D, a familiar challenge here. So in this one, this is one of those questions that doesn't necessarily telegraph itself very well. It asks you if there is a value between 0 and 2 for which f double prime of c equals negative 4. So in looking here, we're talking about f double prime on the interval from 0 to 2. So in a sense, I'm going to kind of lock myself in here. The first thing that my mind thinks about, so we're in my head here. This is my head. My brain has suddenly gotten larger. The first thing my brain thinks about is IVT. Could we use the intermediate value theorem? Because I noticed that there's this information about f being twice differentiable, which guarantees the second derivative is continuous. Looking in here, we're going from 11 to negative 3. Unfortunately, negative 4 is not forced into the middle of those values. So unfortunately, IVT is not going to help us out. So instead, this is disguised a little bit, but this is really a mean value theorem question. And my thought process then is that f double prime is the same thing as the derivative of f prime. So we're going to actually set this up using the mean value theorem. As we've said before, mean value theorem requires continuity and differentiability. And I did a good job of describing these in the written solution, why they're there. But basically, to start my exploration here, and this could be a total stream of consciousness, get everything right on the AP exam kind of question if you did. We start by pointing out that f is twice differentiable. I mean, they told us that. It says so in the question. I told you that. It's in the question. F is twice differentiable, and so that means a bunch of different things. Obviously, we've listed them before. It means f double prime is continuous, but the most important thing is that if f double prime is continuous, that means that f prime is differentiable, because you got to be able to take the derivative of the first derivative to get to the second one. And since f double prime is differentiable, differentiability implies continuity. So f prime being differentiable implies also that f prime is continuous. So right off the bat, we're given continuity and differentiability just from that little guarantee and description in our statement. So at the very beginning, we already know the mean value theorem applies. Our next move is then to think about what the mean value theorem talks about. For an MVT question, our job is to show that the average rate of change is equal to the derivative. But here's the thing. We're talking about the second derivative this time, f double prime. So we want to figure out an approximation for f double prime, which means we need to take the average rate of change of the first derivatives. A really subtle thing, but something that's easily possible here. And we're on the interval from 0 to 2. So we can say now that we want to look and consider f prime of 2 minus f prime of 0. Over 2 minus 0. That's going to be equal to, let's see, f prime of 2 is negative 3. f prime of 0 is 5, all over 2 is negative 8 over 2, which is negative 4. That is exactly what we were asked to prove. So what we've now shown is that f prime is differentiable and continuous, so the mean value theorem applies to the derivative f prime, and the average rate of change of f prime is equal to negative 4. That's all we needed, because now we can invoke the intermediate value theorem. Therefore, by the MVT, and for the sake of time, I am going to literally write MVT. By the MVT, f prime of c, which is equal to f double prime of c, so I'm making sure to establish that it's a derivative, equals negative 4 for some value, which is some value c between 0 and 2. So we've done this question many times before, but I hadn't asked it where I've given you an f prime and asked you to use its average rate of change to get f double prime, but it's a great question there. It's also nice, it'd be also good if you considered the intermediate value theorem as well as a possibility. In this case it didn't pay off, but there are always situations where it might. Okay, and last but not least, I'm going to hit this question as quickly as humanly possible, because I have to go. So in here, we're told that the limit as x goes to 9, which, there's no 9 on the table. The limit as x goes to 9 of some polynomial over f of x plus 13 is equal to negative 5. And it asks us, what is f of 9 equal to? Well, recall, if you're going to evaluate a limit, we always need to check that the limit of the numerator over the limit of the denominator gives us what we expect. So let's just evaluate each of those two limits separately. So we're using a limit property first to see what happens. So if we plug in 9, we get 9 squared minus 7 times 9 minus 18. Excuse me, that's 81 minus 63 minus 18, which is 0. So, we get 0 on the numerator. So already, we know that the answer is supposed to be negative 5, but if we get 0 by direct substitution, that means that there's only one path to getting an actual numeric value out of this. That implies to us that the limit as x goes to 9, the limit as x goes to 9 of that expression up there, x squared minus 7x minus 18 of f of x plus 13, is indeterminate. So when we do direct substitution, we need to get an indeterminate form. In fact, I should say instead of is, produces an indeterminate form. So let's do this. Is an indeterminate form. So that's what we're expecting. What that means is that the denominator, the limit as x goes to 9 of f of x plus 13, that has to also equal 0. Otherwise, we wouldn't have an indeterminate form. Like, take, for instance, the idea that f of x plus 13's limit as x goes to 9 was 7. Your limit would be equal to 0 over 7, and 0 over 7 equals 0. It's only when we get 0 over 0 that we can do some stuff and eventually get to a number like negative 5. So to wrap this up, this is forced. And if that's true, direct substitution should yield 0 as well. So f of 9 plus 13 has to equal 0, and simply put, f of 9 has to equal negative 13. And with that said, it's a really fast answer, but this is a really fast problem. It's all about recognizing indeterminate forms and how you could approach that. And without further ado, although this went a little bit faster, I think this assignment was a little bit more straightforward, with more technique than anything else, less conceptual work. But in any event, I hope this has been helpful, and I hope you have a great night. Thanks for watching.